Let us now begin section 4 of this notebook, Rules of Probability 2, Multiplication Rules. In the previous video, we studied the rules of probability based upon Venn diagram. Here are some examples. If you have a union of two mutually exclusive events, simply add up the probabilities. If you have some overlap, in that case you'll have to decompose appropriately so that you have a number of mutually exclusive events, and then you can add up the probabilities. Or you can subtract away the events that are counted twice. If you apply that principle to complement events, you get probability of the complement event is 1 minus the probability of the original. It can be quite useful. Of course, if you have more complicated situation like 3 or more sets, well, you'll have to apply addition principle either forward or backward. Backward I mean by through subtraction. You get appropriate decomposition and put in all those numbers in appropriate places, and then you'll have to use the logic to get appropriate shading, and then even further application of the addition principle to get appropriate addition or subtraction. As you can see in this answer key, everything is just addition or subtraction. Those were examples of Venn diagram and addition principle. Now we are going to work out another very important visualization tool in probability, which is the tree diagram. And underlying principle is this time multiplication principle. Here they are. Probability of A and B is the probability of B times probability of A given B. Or it can be written as probability of A times the probability of B given A. They are both coming from the conditional probability formula. Conditional probability A given B is equal to the probability of A and B over the condition probability of B. But if you're interested in this numerator, the probability of A and B, if that's what you want to find out, then you'd better flip this denominator to the other side. Then you get the first identity. If you do the same thing from the second conditional probability formula, flip the numerator flip the denominator, to the other side, you're going to get the second formula here. Either way, we get the multiplication principle. And another observation here you can make is it doesn't matter which way you start. Probability of B first and then the conditional probability A given B, or A first and then the probability of B given A. Now what if you have three events, A and B and C? Well, in that case, you have to use this multiplication principle again. You'll have to multiply another conditional probability, the third one, here, and continue. You can multiply the fourth one, fifth one, and so on and so forth. Let's work that out through an example here. Example 4.2. 3 balls will be selected without replacement from an urn that contains 5 red balls, 3 green balls, and 2 blue balls. Imagine an urn with some balls, kind of like this. Well, this is coming from our textbook, of course. We have some chocolate pieces, and even at first glance, I can see that there are more than 10 pieces, and of course, far more than just 3 colors. In other words, this is far more complicated system than the one we are working on. This is far simpler, just 3 colors and 10 balls. Okay, let's stick to this simpler system, and let's work out the first problem. Find the probability that you get red ball, a red ball, and a blue ball in that order. Red, red, blue. Now, how do you visualize that? Here is the visualization tool called the tree diagram. The first draw, we have 3 possibilities, red, green, and blue. And each outcome, we have 3 branches, red, green, and blue from the second draw. And then for the third draw, of course, we have red, green, and blue. And all those will be repeated, all the others over here, down here too, but I found a bit tedious to draw them all, so I decided not to draw them here, but in theory, everything has all those branching. Now, if you follow a appropriate path, this is the probability you're going to get. There's 5/10 probability to select a red ball because there are 5 red balls to choose from out of total 10 balls. Now, next probability is 4/9 because there are 4 red balls to choose from because 1 is already selected out of total 9 because, again, 1 ball is already selected out. You see, it's the same red ball, but the probability is not the same because this is a conditional probability. Right here, the second probability is a conditional probability. The third one is also a conditional probability. Condition is based upon 2 previous events. 1 red ball is selected in the first row, another red ball is selected in second row, so 2 of them are out. So we have total 8 balls to choose from, and out of there we have 2 blue balls to choose from, so we have 2 8. Multiplication principle tells us multiply everything and we have 1/18. And that's how we can work out the tree diagram and multiplication rule. Now, if you use conditional probability notation, you can get something like this. But I've never seen a student who prefer these kind of things. And I'm a mathematician, so I feel very comfortable with this kind of mathematical formulation. But even I cannot say I prefer this. I prefer this one. And of course, I've never seen a student who prefer the other way around, so go ahead with this one. Some students have to have this tree diagram in order to see this multiplication principle, but it is tedious to draw them all, especially there are many. So draw first and the second, and then later on try to get some pattern and then use out the multiplication principle. What if you have red, red, blue, and then green, for example? In that case, you'll get something like this. Red, red, and then next one will be green, right? Okay, there are total now 7 to choose from, and then there are 3 green balls to choose from. And then the answer is not going to be 1/18. It's going to be 3 over 56, and then that's going to be, well, something. You can expand this kind of problem into variety of setting. Oh, by the way, this is not right. I have to get green as well. So it should be green. Okay, that looks perfect to me. For example, if you want red, red, blue, green, you can use this multiplication principle once more and then get this kind of computation. If you select one more and then the next one is red, then what you're going to get? Multiply one more, and then there are now total 6 to choose from, and then only 3 red ball left. And then let's see. Okay, I give up. This is rather complicated number, so you'll have to work out with your calculator. In any case, finding out the probability using this tree diagram and multiplication principle is not a difficult one once you know how to take the first step. Okay, now let's go over to the next problem. Find the probability that you get 2 red balls and a blue ball in any order. So it can be red, red, blue as part A, or red, blue, red, or blue, red, red. Are there any other ways? No, not really, those 3. And how do we work out? Well, just a multiplication rule. Here's the first one, 5 10, 4 9s, 2 8. And the next one, 5 10, that's the first draw. And the second draw, well, there are total 9 balls to choose from, and then there are total 2 balls so to be selected. So we have 2 9. And the third one, there are only 8 balls to choose from, and there are 4 red balls left. Similarly, we can get the third computation. Now these 3 are mutually exclusive, so you can add them up, and you're gonna get 1/18 plus 1/18 plus another 1/18. You're gonna get 1/6, something like this. So addition principle applies at the very end. By the way, here's a visualization for the second computation. This one, RBR, goes kind of like this. First row is red, so red, and then the blue path, and then the red path. I could have drawn the third one as well, but I found it rather tedious. By the way, the answers are all the same because the multiplication is commutative. The denominator is 10 times 9 times 8, and the numerator is 5 times 4 times 2, maybe in different order. In any case, the same value. Now let's work out the final problem here. Find the probability to get at least 1 red ball. At least, so it's going to be either 1 red ball, 2 red balls, or 3 red balls. You have to add them all up. But not just that. 3 red balls, that's red, red, red. Okay, I can find out. 5 10s times 4 9s times 3 8. But the next one is red, red, blue, red, red, green, or red, blue, green, or, oh my, there are too many. How do I list them all and find out? It's gonna be an enormous task. Not really, if you get a little bit clever. Look at the complement event. At least 1 means 1 minus no red. Look at the complement. Probability of at least 1 red is 1 minus no red. So the first row has to be non-red. The second row also has to be non-red. Third row has to be also non-red. What do we get? Same multiplication principle as before. 5 10s times 4 9s times 3 8, because there are 5 non-red balls out there, either green or blue. This is a great example of the complement principle in action. Okay, let's now consider other kind of multiplication principle, especially if you have an independent event. In other words, event A and B are, well, literally independent, they are unrelated. In that case, the conditional probability B given A and original probability B are the same. Likewise, the probability of A and the conditional probability A given B are the same. In any case, we end up with probability of A and B is equal to probability A times probability of B. When do we have that kind of situation? Here is an example, example 4.4. 3 balls will be selected with replacement this time. So what do we get? Get a ball, record the color, put it back in, shuffle it, and get the second ball, record the color, put it back in, and repeat this. Because the ball is back in, so the total number and the color distribution remains the same, and same randomness and so on. So the second row and the first row are the same. Third row, fourth row, 100th row, they're all the same. Yes, we have only 10 balls, but we can do this 100 times too because we are doing it with replacement. And we have straight ahead multiplication principle, so we have just this computation. No reduction in the total number. So 5 tenths times 5 tenths times 2 tenths. Simple. Even simpler than before. What if we have 2 red balls and 1 blue ball as before? The same thing. 5 tenths, 2 tenths, mixed up in terms of order of multiplication. In the end, you get the same answer, and then add them all up, we get appropriate probability. By the way, if I try to visualize, we're going to get something like this. So same kind of path, but, well, each branch is actually equivalent this time as the very first one. The fourth problem is left to the students.